Right, hello again, everybody. This is webinar number 81. Don't worry about the 81, it's just number one. And this is dealing with the very important idea about observational skills. And this week, I'm going to be talking about the general sort of regulations and things to avoid and what to do, etc., but also looking and focusing on the naked eye observations. And then next month, Alistair, as he mentioned, will deal with the aided observations. We'll explain a little bit about those if you're new to this in a moment or two. So I'm Nigel Marshall, and we're going to have a look at this very important, very basic webinar on the requirement from Edexcel, the observational skills. And I'll tell you why they're really important a little later on. It is not just important, it is actually a requirement from the GCSE specification that all candidates must complete as a minimum 2 observational skills projects. One of them should be unaided, in other words, with the naked eye, and the other one should be aided, in other words, using a telescope, binoculars, a robotic telescope perhaps, camera. So it's not helped, aided and unaided, as somebody thought in a previous year. It's aided as opposed to unaided using an optical instrument. So I hope that clears that little bit on there. Right, okay, what have we got here? This is straight out of the specification, just to show you how important this is. I know it's early days in your course, but it's important to have the 15th of April 2026 or 2027 handy because the observational projects must be verified, must be signed off by your tutor prior to that date. And it says underneath that this is the minimum requirement. So students should be given every opportunity, and I really encourage this, to develop their own observational skills. I mean, this is astronomy, it's an observational science, isn't it? We don't really do many experiments like we might do in chemistry or physics. Okay, 1 or 2 space probes have gone to comets and gone to moons of Mars, and they brought back or collected samples, but not really as much as the volume of observational skills. Everything else basically is observations. And these could well be tested in either paper 1, which is all about naked eye astronomy, or paper 2, which is all about aided astronomy. Paper 2 is basically astrophysics. So that's just a little bit about the requirements, albeit being early days for that. But it does give you a chance to show how astronomers work. And again, I'll have a little bit more to say about that in a few moments. If you have any questions, by the way, I can't see those and do this presentation at the same time. I'm not great at multitasking, but either Alistair in the back room will answer queries, or I'll answer them at the end. Or if you forget and the webinar is over, then you can email me. Not a problem at all. Right, so let's have a look at what kind of things we have to do to demonstrate that we can plan a series of observations, we can actually carry them out and record them, we can analyze our results, and we can evaluate the whole project so that next time we do it better. And this is what astronomers themselves actually do. There are 2 lists, A and B, and list A are naked eye projects, and list B are aided projects or tasks, they call them in the specification. If you can't read this, I'll just mention A1, demonstrate the changing appearance of lunar features, and that's what you have to do. Look at the changing appearance of lunar features. Here is a series of naked eye drawings of individual lunar features to demonstrate the changing appearance during the lunar phase cycle. Right, I would avoid that one. If you've got human eyes like I have, I can only see light grey and dark grey on the moon, the highlands and the seas. I just can't see anything else. Maybe Tycho, the great big crater close to the south pole of the moon, but I'm struggling. With binoculars or my small telescope, I can do B1 instead of A1, demonstrate the changing appearance of lunar features, but using photographs or a telescope or your camera, doctoring the images to emphasize contrast, dynamic range, which is basically the difference between the brightest part of the image and the dimmest part of the image. And that's a nice one to do. As is B2, finding the radiant of a meteor shower. So you need a meteor shower for that. It's actually possible to do it as a naked eye project as well as A2. You can see the titles are the same, but A2 is naked eye and B2 is aided. Now you can't do both A2 and B2 because basically you're doing the same thing twice. So they have to be different numbers. You have to have one project, just looking at the bottom of the screen now, from list A, and one project from list B. So the numbers must be different. So you can't do project A2 and B2. You can do them both for fun if you like, and just submit one of them. But for the requirements of the exam board, we need to have different projects. I think you can understand the reason for that. Now, you'll need to record everything. And I get questions about what's the format for writing these up? And there isn't one. You can write it up as you wish. You can submit it on paper. You can submit it as a series of email attachments. You can submit the observational skills as a series of PowerPoints or something like that. It's entirely up to you. But what I would recommend is that you just keep a diary and put your observations and your plans and your doodles and everything else that you want to record, and you put it in a kind of diary. Not ready-made, just sort of page one, open the book up. It might be October the 15th. So the date is October the 15th. And you can say it was really clear that night, and therefore you went out and observed blah, 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 because you planned to observe them. So more about planning in a little while. So make sure, again, just a little provider here, that you are carrying out observational skills and observations basically supervised. So with all the kind of health and safety regulations, astronomers, naked eye astronomers, even those using telescopes, go outside in the dark. There's 101 trip hazards, and it's very cold sometimes. So again, the weather conditions tend to put some astronomers off a little, but don't be put off by that. Now, this bit about the cyclic idea and the rationale behind the observational skills. The specification, it says, quite rightly points out that observations is an iterative cycle, round and round and round, of design, observation, analysis, evaluation. All of these terms I'll explain in a few minutes. And that through the evolution, going from designing what you're going to observe to actually observing, and then doing something with those observations, analysis, and then evaluating a little bit more than, I enjoyed doing the project and it was a bit cold, but I managed very well. We don't really want anything quite so simple as that, although it would actually qualify for an evaluation. But through that evolution of those four aspects of the observational skills, students should be suggested improvements to form the basis of the design of further observations. In other words, having gone through that little cycle, students should be in a position in the evaluation to sort of think, right, how can we make this better? How can we get results that are much clearer? Even if it's only, how do we avoid getting a blurred image this time? How do we avoid taking observations when the moon is full, which isn't very good. So, we're learning by not by our mistakes really, but we're learning on previous ideas. Okay, I hope that makes sense, everybody. I'm just trying to justify, as I say, why carrying out observational skills is extremely useful. And by the way, you've no need to carry out a complete project. You can just do a practice plan, if you like, just to get used to the ideas of what these observational skills are like. It can't count towards the official document, of course, but you could nonetheless plan some out. And there's some exam questions in past papers that ask you to do some analysis, comparing how many stars there are in an area of sky in the plane of the Milky Way and out of the plane of the Milky Way. So you can use that data and you can actually do an observational skill, which is actually one of the exam questions. Okay, so as mentioned, and these need a little bit more elaboration, excuse me, there are 4 parts in each project and they're all as equal as each other. So it's not the observations that are, you really want to impress somebody, you really want to impress somebody anyway, but not just by the observations. You want to impress somebody, whoops, I don't know what's happened there. There we go. You want to impress somebody with the design, with the actual observations themselves, with the analysis, which could be just a description of something, or it could be some calculation. So you might be observing the features of the moon and might want to try and roughly estimate the height of a crater or something like that, a big crater like Tycho we've mentioned already. And then to evaluate. And this goes round in a whole cycle. You might only go around it once. You just do a design, make some observations, analyze them, evaluate the observations. Fine, that's it. You don't need to actually carry it out again with your suggestions for improvement. Right, so let's have a look at these in a wee bit more detail. Oh, there we are. Somebody just asking there, do all the 4 parts have to be from the same project? The ones that you are going to submit to your tutor for signing off to say that you've done it, yes. But if you want to do what I call singles, if you just want to practice an evaluation based on some results, based on some observations, that's absolutely fine. Oh, and by the way, all the observations have to be your own. Don't think I put that in anywhere when I was just checking it this afternoon. So all the observations have to be yours. You can compare them with images from other telescopes and so on, but yeah, it has to be your own observations. Don't know whether we've got a question of that in the chat. There we are, diary style format, but you can ignore my advice. It's only a recommendation. You don't need to do it like that. But when you're planning, and this is where people, I think, make the initial mistake. You've got to produce a list of lists. Lists are very important in observational skills. Lists of targets of what to observe. Tycho crater, Orion's nebula, the great Andromeda galaxy. Those are targets. Observing locations, dates and times, and instruments, that's obviously for the aided set of tasks, so that you can select with astronomical reasons. An astronomical reason is not, I'm going to observe the plough because it's my favourite asterism. That's not an astronomical reason. The fact that it's visible all year round, the fact that it's pretty high in the sky for most months, they are astronomical reasons. And then you're going to write down a program that'll help you to achieve the tasks that you've chosen, bearing in mind, as we talked about, health and safety. You might think this is a bit strange for a plan, but very few students Actually write the plan in the future tense. I will do this, I'm going to do that. A week on Tuesday, I'm going to see if the weather is good enough, blah, 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 blah. Future tense, please. It's no good saying, we'll look at an example later. I did this and I did that and I did the other. Well, that's not a plan, is it? Future tense, lots of alternative targets and dates and times and locations from where to observe. So we want lists and alternatives. I usually make lists and tick and cross and then narrow, say, the observing site down to about two, and then finally plump for one. So I might be observing from ideally Kielder Forest in Northumberland. That's a wonderful dark sky park. I might be observing from the Lake District somewhere, Ambleside, let's say. Not quite as good because there are a lot of buildings there and there's mountains in the way, and you don't get that in Kielder Forest. I'm going to go in on a local hill. I'm going to go on Phoenix Hill, where there will be a little bit of light pollution and I won't be able to really distinguish stars and faint objects near the horizon. But it's close to home anyway, as opposed to the others, which are going to be a 7-hour drive. I could observe from my back garden. Problems there. Mostly with glare, mostly with kitchen lights being switched on. Or I'm going to observe from my bedroom window. Now, there you are, 5 possibilities. Astronomically, I think a couple of those are just sort of close to home, and I wouldn't really be expecting you to. I don't think you'd be wanting to do observations sort of from out of the bedroom window or from a skylight or something like that. I think probably Kielder Forest is a little bit out for some of you, although it's on the doorstep for 1 or 2 students we've had before. That really does produce some great dark skies. Almost too dark, almost too many stars sometimes, you can see. So, yeah, this is important because people don't do this. They don't listen. They don't realize that this is a plan. You're planning for something in the future, not in the past. So, I'll shut up about this. Alternatives enabling you to select your location, date, times, and so on. And it says here, many plans need to be rewritten because they're presented in the past tense. Now, all right, your observational skills write-up are not assessed at all. There are no marks. It doesn't really matter the quality of your observations and your write-up. It doesn't matter. It's ticking boxes, basically, for the exam board. But I think you'd like to think that since you're studying astronomy and there's an opportunity to develop some observational skills, that you might want to have a good go and do a nice actual project. Remember, you could be asked something similar in the exam. Not all 4 categories, just one of them. Right, so enough said about that. Lots of resources. We've got planispheres and stellar maps. We've got lunar calendars, which are great, showing how the phase of the moon changes through the lunar month. That's very important, of course, because you don't want to be doing much observation of faint objects in the sky. Let's say you are trying to observe with the naked eye some double stars or something like that that have appeared. You don't want the moon to interfere because you're going to have very narrow sort of field of view. The moon's going to drown out a lot of observations. So yeah, first 5 or 6 days of the lunar cycle, like you can see on the top line there, and the last 5 days, they're great. But if you want to observe the moon and carry out a very important experiment that Aristarchus of Samos carried out, which was determining the relative diameter of the moon compared with the relative diameter of the Earth, then you really want something close to full moon. Top row, second from the right, I think. And we've got various apps and so on. Again, these tend to give too much information. If you've gone onto Stellarium, by the way, and you've started having a play with this, there's an important little box on the right-hand side called Stars. I think you have to access it from the left-hand side of the screen. But it allows you to select the sort of dimmest star and what its magnitude would be. And I would go to about magnitude 3 or 4. Then you're not absolutely blinded by lots and lots of irrelevant information, satellites and deep sky objects. We're not going to be dealing with deep sky objects with naked eye observations. So lots and lots, and you'll have your own favorite resources, and I do too. Right. I think we'll get on to the observing in a minute. Yes. Really, your observations that you sketch, remember this is naked eye. So it's pencil and paper, plain paper, perhaps with some constellations or some bright stars already put on there so that you can show where meteors occur, and you can draw a meteor streak and several of these, and you're on the way to finding nice project, this one, to finding the radiant of a meteor shower. So all the meteors, all the shooting stars appear to be coming out from a single point. It's all because of perspective. They're actually traveling, the actual particles that will burn up. They're actually traveling more or less parallel to each other. A bit like cars on a motorway. If you go on a motorway bridge, you see the cars coming from some vanishing point, as it's called. But they're not actually diverging away from each other. They're traveling parallel. Techniques, you can show off a bit. You can show off that you know what dark adaptation is and averted vision. These are all features that are referred to quite early in the course. And make sure that you record all the dates and times and weather conditions and seeing conditions. And there's just a reminder there, the teacher telling the class, don't forget to record everything in your diary style notebooks. Although it's no need to be diary style, you can just use any old notebook, preferably with some blank sides, not lined, and also perhaps with some graph paper, although you can stick these in at a later date if you're plotting a graph to determine your longitude, perhaps in one of the shadow stick experiments. That's a nice one to do. It's using a shadow stick to determine longitude. Brilliant. Really popular project. When we're analysing, these are the sort of things that we want to look for. So you might be, as I've just mentioned, presenting some numerical data in a chart, a bar chart, or a graph, a line graph with crosses and a scale, and so on. So you might have a graph of shadow length against time, and you should be looking for a kind of deep letter U shape when you plot that graph. Then you can determine the bottom of the graph and then do things with that. You might be wanting to perform calculations. I did mention earlier, maybe estimating the height of a lunar crater while you're doing your lunar observation project, and to appropriate number of significant figures. Yeah, it really it really annoys me sometimes when people write 17 significant figures. I found my longitude to be 3.1689420 degrees west, and my latitude, it's not that. You're quoting your latitude to about on the ground, the nearest millimeter. I would have thought the nearest 10 kilometers would have been plenty. So just watch that you don't go overboard with significant figures. They're not really all that meaningful. We might be simply describing something in an image. Again, this might be more relevant for the aided observations, maybe using a robotic telescope to look at the moon and to compare the appearance of craters at different illuminations. So that's quite a nice thing to do. Or you might be just identifying a pattern in a series of drawings or photographs. You might be using, in one of the aided projects, you might be using a projection of the sun to look at sunspots and to determine the time it takes for the sun to rotate once. That's a nice, very satisfying project to do. And you can really be very, very clever. One or two students in the past have been real wizzos with image processing and so on. And they've stacked images and taken different colored images and put them together and really impressed, almost professional astronomy by some. It's no need to be like that. But if you want to, go a little bit over the top, then we're not stopping you, we're encouraging you. Good. And then finally, this is the evaluation. It's going to be good to say how accurate you've been. So if you get your longitude within about 1 degree, I'd be quite happy with that. If you determine your longitude by about 10 degrees, so that you are in the middle of the North Sea somewhere, maybe we could just check those observations and just see what might have gone wrong. If we find our longitude to the nearest point 001 degree, then that's just crazily too precise. Sometimes we're calculating something and it might be useful to look at the percentage error or the success rate, as we say. So you might get, say, let's take a very, very simple example. You might be at 8 degrees west longitude, and you might have worked out that you are at 6 degrees west longitude, which isn't too bad. It's only 2 degrees out. But if you work that out as a percentage, 2 degrees over 6 degrees, the true value, is 33%. So there we go, 33% success rate. So that's a nice kind of way of finishing off a project. Oh, I've done this, I've done that. I'm now going to just assess how successful I've been. And you could identify errors. I observed when the moon was full, and unfortunately, I couldn't see many stars to be able to estimate their magnitudes. So one asks, why did you do the experiment when it was full moon? Not ideal. We've got to identify sources of error, and we could perhaps just say a little bit about sky glow or glare. Now, if you're just starting the course, that I think one or two of you are, you'll learn about those in more or less the first couple of weeks. So they are in chapter 1, all about the Earth's atmosphere and the Earth's structure as well. So sky glow is the orange stuff around the horizon, and glare is somebody shining a torch in your face. You lose any what we call dark adaptation. All right, got those the wrong way around. I've just got the India evaluation. Right, and that cycle of events trying to improve the original observation programs. Now, if all this sounds a bit complicated, I'm trying to put in as much as I can. What we've got in these white boxes is basically what is in the introduction to observational skills that you got either from Alistair or from myself when you were sent information about the course. So you can always use that as a nice reference document. Introduction to observational skills. What I've tried to do here is just blend them in so that they don't look, it doesn't look too formal. This, we want to, we want to encourage students to go out and do some observing. Having planned and having thought about the eventual analysis, that's great. Okay, so that's the end of part 1. For part 2, which will be shorter, I've copied parts of an observational project that was a real project, and it was submitted by a student, it looks like in West Yorkshire, And this student allowed the exam board to make this public. So we're not pinching anybody's results or anything like that. The whole project isn't here with no names or anything like that. I'm going to be a bit critical. I think you'll realize why in a few moments. This is a real project with all 4 parts. Okay, are we ready? Seatbelts fastened. Right, this student has written it in the past tense. So it suggests that he or she hasn't really planned this out at all. I planned to draw 3 different constellations. So I suppose in the past, he thought, I'm going to draw 3 different constellations. So we'll let him or her off then. On the 7th of April. Now, why the 7th of April? Was the moon new? In which case, most of the objects in the night sky can be seen. Was it his or her birthday, which isn't really an astronomical reason? And again, 3 constellations, Ursa Minor, Ursa Major, and Cassiopeia. No reasons for those 3, although good choices, because Ursa Major and Cassiopeia certainly, the shape of the W, it makes the pattern of stars that represent Cassiopeia really clear. These are constellations, but constellations, I think the student wrote on another page that I didn't include, that they were patterns of stars. You'll learn early on in the course that constellations are areas of sky containing stars, comets, galaxies, nebulae, and so on. So the constellations are not the patterns of stars, but scientists, not scientists, astronomers, early observers, used the patterns of stars to name the constellation. So these 5 stars looks like an Ethiopian queen, so we'll call it Cassiopeia. The student's going to make observations from 9:45 p.m. to 10:30 p.m. from Ilkley Moor in West Yorkshire at a latitude of 53.92 degrees, getting a little bit precise there, and a longitude of minus 1.75 degrees should be in there. So this person isn't really being very scientific, because the latitude and longitude need degrees symbols. They're a wee bit precise, and they should be north and West Yorkshire and west. So the latitude is actually 53, I'd call it just 54. I'd just forget the 0.92. Latitude 54 degrees north, longitude 2 degrees west. I'm rounding my 1.75 to 2. If you think that's a bit harsh, keep it at 1.75. But let's put degrees in. And the student will take the observations from here, so from Ilkley Moor, because light pollution won't affect my view of the sky, and I'll be high up. Right, so this is presumably some reference to sky glow, and obviously the student has chosen or will choose 3 constellations that are actually quite high up, that have quite high, what we call altitudes. So I don't think the orange glow around the horizon will affect things too much, but it's worth mentioning that. That's quite nice. But no lists, you see. No alternatives, and that's really what your verifier, so your tutor will be looking for. And this person checked the weather forecast for the night, typo there, we can all do that, and it was forecasted to be clear. Right, okay, not much, I think you'll agree, not a great deal of astronomy in there. I'm going to do these on the 7th of April. I'm going to look at Ursa Major, Ursa Minor, Cassiopeia. I think the student's going to estimate their magnitudes, how bright they appear, and compare it with the magnitude that is in, in a star atlas or something like that. Right. Well, I've been a little bit harsh on the student there. I've tried to point out one or two good things, but he or she hasn't really given reasons. You know, they're great constellations. Ursa Minor is a bit faint, but Ursa Major and Cassiopeia, great, easily found. So you're not spending 15 minutes looking at the sky and trying to find out where they are. So Ursa Major is obtained from Plough, which is a asterism, that is a pattern of stars, and Cassiopeia is identified from the W, the rather wobbly shaped W, and again, that is a asterism. Good. Move on. Oh, we've got a bit of history now. So here we go. Ursa Minor best seen in June. Why? Why is it best seen in June, I wonder? I think in June, I think it's going to be not dark till about 3 a.m. and the sun will rise again at about 5 a.m. Ursa Major, one of the original 48 constellations listed by Ptolemy, best seen in the month of April. Why? I'm not quite sure why these are in here. Ptolemy was an Egyptian astronomer who lived around 150 AD. Right, it's interesting. Oh, and I chose the constellations as they were all circumpolar. That means they don't set. They actually go around the north or the pole star, or appear to do. It's actually nothing to do with the sky rotating. It's the Earth rotating. And a good reason. You can see them anytime when the sky was clear. So there we go. I like the last little paragraph there. I don't really think I need to know. And I'm just querying the accuracy of the earlier bits there. I wouldn't have put all that in if I was writing this. Right, now this student has produced some charts, some diagrams of what he or she has seen. This is on the 7th of April, 2011. Gosh. And this is Ursa Minor, and the time is 23:10. So you see the observing conditions and the date and the time have been recorded. The scene conditions are given a Roman numeral from 1 to 5. And you learn about scene conditions, which is all to do with the steadiness of the air, or whether the air is turbulent and you can't really see things too much. They keep moving their position. Bit of cloud cover on the southern horizon, otherwise clear. Right, so there we go. Now, what the student is going to do, and he or she hasn't written this in the account, is to sketch the constellation, or rather sketch the stars in the constellation and estimate their magnitude. Now, I can see that these have been done far too precisely. It makes them meaningful in a way. 4.00 for delta at the top there. 2.02. Now, really, if you are going to study magnitudes with the naked eye, with sky glow and a bit of glare maybe, the nearest whole number, I would encourage this student, would suffice. Magnitude 2 for alpha, magnitude 4 for delta, 2 not attempted. Eta, the bottom left-hand side there, looks like half a paper clip. Magnitude 5, that's lucky to be seen. Look at beta on the right there, magnitude 2, and gamma, I think it is, though it looks more like a seagull that a child would paint, magnitude 3. That would be much more sensible to me as opposed to 2.02. You see what I'm getting at with these significant figures? You can get too significant figures, too many, and it's not impressing anybody. It's just going over the top of it too much. Now, what the student has then, there are other sketches as well, but I didn't want to really extend this way out into post 7 o'clock. We did say 10 to, didn't we? We're going to be very nice on that. Now, here are the results. So we've got a table of results, which is great. Now, we've got, quite complicated this. The constellation is Ursa. I don't know if it's Ursa Minor or Ursa Major. I don't... Polaris we've got. Oh, as a reference star. Yeah, what the plan is is to sketch the stars, to estimate their magnitude with reference to nearby stars, or what we call reference stars, usually 3 or 4 of them. We've only got 1 here. And then we can compare the estimated magnitudes, the observed magnitudes, with the true value. And again, what I would do is not to be so precise. So Alkaid, magnitude 2.00, let's call that 2. Let's call the actual magnitude 2, because these numbers do vary a little bit depending on the sky conditions. So I would say that's not a difference, that's a spot on. My magnitude estimate 2, actual estimate of eta is 2 or even 1.9, but 2 will do, and then the difference of 0.1. And 0.1, I think the calculation's not been quite rightly done here. Difference of 0.1, oops, let's see if I can't get my calculator on. 0.1 divided by the actual value of 0.9 is actually, 5%. Right. That's because the actual value isn't very large. But in my criteria, you see, my magnitude is 2. The actual magnitude, the nearest whole number, is 2. Spot on. I think what the percentage difference is, I think the student has worked this out incorrectly. I think really they want to write, not sure what, I've not looked at this this project for quite a while. I think the percentage difference is 5%. So the actual observations really are correct. To 100 take away 5, they are 95% accurate. And so on anyway. I'm a little bit confused. I would like to have a bit more information. I'd like to know which stars were used as reference stars, but it's a good attempt. Nothing brilliant, nothing really awful. I know I go on about significant figures quite a bit sometimes. Now, we should have some analysis here. No, we've got the analysis in the table. Evaluation. Here we go. Let's have a look at this. Reviewing my drawings, I was happy with 2 out of the 3 of my drawings. Right. Well, the drawings are actually very good. The actual sketches, they do look like the patterns of stars that are being representing the constellations. I was not so happy with my Ursa Minor, capital S is needed, drawing. I was unsure whether it was correct or not, as the stars in Ursa Minor are a lot dimmer on average than those in Ursa Major or Cassiopeia. Well, why did the student use those then? Why did the student plan to observe a faint constellation? And this is where the planning, this is where the selection. So you can reject Ursa Minor from the list of maybe 7 or 8 constellations because it's too faint. And that's an astronomical reason for not including it. So after evaluating my estimated magnitudes, I felt that within 0.2 magnitudes, I'm ignoring the 0, was okay. I would say for an observation project, 0.5 magnitudes would be great. Half a magnitude, stars go from about 0 down to about 6. Now, the numbers are higher, but the brightness goes down. So this is a strange thing with magnitude of stars, as you'll find out in the course. Lots of strange ideas in astronomy because it's steeped in history. It goes back till antiquity. So the brightest stars have magnitudes of 0 and 0.5 and 1 and 1.5, and the dimmest stars 5 and 5.5 and 6. I think nearest half a magnitude would be acceptable. So I was quite disappointed after following this guide. I don't know what that means. To accuracy to find that the word processing has gone a bit strange here. I don't think AI could kick in 2011, but it was bang on the magnitudes on 3 occasions. But I had used one of those stars for reference. The other magnitudes I got right was a well-rounded number. What, 0? I don't understand what that means. Sorry, I can't help you there, everybody. And there's some idea about success rate at the bottom there that's quite nice. A nice little bit to just put in. So here we are, a little bit more on the evaluation. I thought that on average my estimates were good. Yeah, they are, because I was within 10%. Now we're getting to sensible ideas, 5% and 10% and 50%. Much better. The overall average could have been lower. It was let down by my Ursa Major estimates. Okay, I thought they were pretty good from what we saw. It appears that I've only really been let down by my Alioth estimate. No, we'll have to go back to the project to see what that means. The brightest stars that I saw on that night were 1.80 magnitudes, and they were Dubhe and Alioth. The dimmest star was something I can't pronounce. Anwar al-Farkadan. Don't know that star, I'm not familiar with that. It's probably because it's dim. It's got a magnitude of 5. 4.95, the books say, but 5 will do. But from the top of a moor above 3 towns isn't that bad. I'm presuming that the student there is trying to tell us that given a little bit of light pollution, he or she is very lucky to actually observe Anwar al-Farkadan with a magnitude of, I just put it as 5. And then a couple of observations, a couple of improvements rather. I could have measured the distances between the stars better. Distances between them, I'm not quite sure what is going on there. Could have measured the distances between the stars. There's nothing in the project about that. So has the student got a ruler at arm's length and seen how many millimeters there are between, say, the alpha star and the beta star, the next brightest one, and then transferred that onto paper? I don't know. I can't help you there. But it was more elaborate. That's a pretty good idea. And I could have used different size stars on my drawings to show different magnitudes. Yeah, that would be good. That's a good idea. And there we are, everybody. That is a few hints and important ideas about observational tasks. So good luck with them. Start early. You must start early. All right, otherwise you'll get panicking and thinking, oh, I haven't done anything, and it's the January before I have to give them in the April. Avoid that totally. We don't want to cause any stress. Practice. Do some singles. All right. So it says, don't forget, you need to complete one project from list A, naked eye, as this one has been, and one from list B. Not the same number. Please record all your observations and all the observational details. Date, time, phase of the moon, seeing conditions, weather conditions, like that student quite rightly put in there. And yeah, practice some singles, such as just the planning stage of a project. In other words, take these ideas and rewrite it as a plan with reasons why you would observe here, there, and so on, which constellations you would choose from a list of, what did I say earlier, 7 or 8. And in the aided project, you'll have also to select from a list of observational instruments. But I'll leave that till next week, till next month rather, when you're with Alistair. So thank you very much, everybody, for coming to the webinar tonight. There are some really important webinars, really stressing and going through again some very, very important topics. Once we've looked at observational skills, we'll be looking at some of the mathematical skills that are needed. Now, this isn't to do calculations, just like I did a few minutes ago. This is really to sort out angles. If this star has an altitude of so many degrees from this location, what will its altitude be at that location? So you're going to have to do a little bit of sort of thinking in your head and thinking on the spot. So those are the mathematical. It's the mathematical and deduction skills really that are very important. And then finally, we're going to have 4 months looking at last year's paper, and it does need that amount of time to go through the to go through the answers and also to look at common errors that students make by not reading things properly and so on. So look forward to having your company again at some stage in the future. I'm going to stop scaring, yeah, as well. Not even a Halloween yet, is it? I'm going to stop sharing the screen. And I hope you found that really useful. Any comments in the